Hello, this is a PowerPoint presentation for the cylinder lab conducted in the AERO wind tunnel on October 31st.
I'm Elliot Kane.
I'm Alejandro Navarro.
And I'm Satre.
The image shown on this slide is a photo which was taken during the experiment while the fan was set at 200 RPM. The airflow shown at the system is traveling over the upper half of the cylinder, and the boundary layer from the cylinder can be seen deflecting the flow from touching the cylinder surface. The boundary layer is a gap that can be seen from the flow and the cylinder body.
Here is a slow motion video of the unsteady vortex shedding that happens behind or in the wake of the cylinder. This is a highly unsteady flow, and through this slow motion video we were able to capture the frequency of the vortex shedding.
The Struhal number represents the ratio of the inertial forces due to local acceleration to the inertial forces due to convective acceleration. Using the frequency from the previous video, the Struhal number for this cylinder at 200 RPM was calculated to be 0.2842, which is considered an intermediate value. Intermediate Struhal numbers are characterized by unsteady flow with frequent vortex shedding.
This slide shows the three different coefficient of pressure plots that were calculated using the static pressure taps along the cylinder. And at 0 RPM, this graph isn't that meaningful because there's no flow through the wind tunnel, and the values are just really random. But once you get to 350 and 600 RPM, the plots begin to become more meaningful. You can see that the experimental coefficient of pressure matches closely the theoretical for a certain region of the cylinder. That region is from 115 degrees below the leading edge stagnation point to 115 degrees above the leading edge stagnation point. That point where it deviates is where the flow separates from the surface of the cylinder, which is an important characteristic which can be changed by roughening the surface, which we'll get to later on.
These images are the plots for the coefficient of drag versus the location around the cylinder, each plotted for their respective fan RPM. The coefficients of drag were calculated through numeric integration of the calculated coefficients of pressure. The plots are scatter plots of the drag coefficient over the 100 different samples that were taken for each RPM test. For the 0 RPM, the coefficient of drag is centered about 0, but there are some outliers which are the result of random fluctuations in the air surrounding the cylinder. For 300 RPM, the coefficient of drag is positive and nearly constant over the 100 different samples. The mean coefficient of drag value for the 300 RPM test was 1.55. For 600 RPM, the coefficient of drag is also positive and nearly constant over the 100 different samples. The mean coefficient of drag value for the 600 RPM test was 1.39. These values are reasonable and compare well with the coefficients of drag obtained in an experiment by Gao, D. et al. They found that the coefficient of drag over a cylinder was around 1.14, which is similar to our calculated value.
Unfortunately, we weren't able to modify any changes to the roughness of the cylinder. However, roughening the surface of the cylinder delays the flow separation from the surface of the body. As seen from the video in the previous slides, the flow separation can be seen occurring directly above the cylinder surface. If the surface of the cylinder would have been modified to be rougher, this would have caused the flow separation to occur a bit after the section above the cylinder. Increasing the roughness of the cylinder also increases the coefficient of drag. Correlating this to the delay of the flow separation makes intuitive sense due to the flow being able to stick to the surface for a longer duration, generating a higher drag force on the cylinder, thus augmenting the coefficient of drag.
One practical application of tripping the boundary layer can be seen in a cricket ball in the image on the screen. There's a seam around the circumference of the cricket ball. And the bowlers use this to produce a sinking trajectory when they throw the ball. The seam trips the boundary layer, and if the bowler grips the ball in the correct orientation, the spin of the ball will produce a negative lift force. And addressing the question, is the flow over the middle of this cylinder actually two-dimensional, as the experiment is designed to produce? This probably isn't the case, because it is likely that the wall, the boundary of the wall, affects the flow. Oh, jeez. The wall effects produce a boundary layer which increases over the length of the test section, and this will change the airflow over the middle of the cylinder. It'll compress the flow, and while at the middle of the cylinder there will mostly the flow will be mostly two-dimensional. There will still likely be three-dimensional effects present. And here are our references. Thank you for listening.